Students, myself Shivi and Dr. Kiran Yadav. In this session, I will discuss about vibrational spectroscopy and vibrational modes. So let's start with the introduction about vibrational spectroscopy. A key experiment technique used to probe the vibrational modes of a material. Raman spectroscopy is commonly used in chemistry to provide a fingerprint by which molecules can be identified. It can be used to explore relative composition of a material, that is, relative concentration of a known compound in a solution. It is widely used in industry and quality assurance, and it is one of the key techniques in the area of condensed matter research. First, let's understand the simple harmonic motion of atoms. Atoms are connected via chemical bonds, which are equivalent to masses connected by springs. We can describe these using Hooke's law. Here Q is displacement of an atom away from its equilibrium position. So from Newton's second law, we can write F is equals to kq, and F is d square q by dt square. So the equation reduces to d square q by dt square plus kq is equals to 0. On solving it, we get the solution as the equation written there. So this was the classical description of simple harmonic oscillator. Now let's move to the quantum description. If two nuclei are slightly displaced from equilibrium position, then their potential energy can be expressed in the form of a Taylor series. So this is the Taylor series in which the potential energy is expressed. We are not interested in absolute potential, so we set V0 is equals to 0. At equilibrium position, dV by dx is equals to 0. Providing displacement is small, third order term can be neglected. We can therefore write Vx is equals to half kx square, where k is d square by square. We insert the potential, this value of potential, into time-independent Schrodinger equation, which is this, and we find the quantized solution for energy. This creates a ladder of vibrational modes. So in case of harmonic oscillator, the potential is half kx square. The energy of quantum mechanical harmonic oscillator is quantized and limited to the values A is equals to n plus half E. Vibrational selection rules dictate the harmonic oscillator transitions are allowed only for delta n is equals to plus minus 1. So molecules can have different vibrational modes. Mode frequency dependent on mass of atoms, bond stiffness, and type of vibrations involved. The type of vibrations involved can be stretching, rocking, breathing, etc. So in figure you can see the molecules in normal position. Then in the second diagram you can see the asymmetric stretch mode. In the third diagram you can see the bending mode. In the fourth diagram you can see the symmetric stretch mode. Now let us consider the light and molecule interaction. During the interaction between light and a molecule, the incident wave induces a dipole P, which is given by this equation, where alpha is polarizability of the molecule and E is the strength of the electromagnetic wave. The EM field of an incident wave at angular frequency omega 0 can be expressed by using this equation. So these are some more equations, but these are not so important, so you can skip these. So let us see one important thing, which is Raman scattering. Raman spectroscopy is a form of inelastic light scattering. Photon interacts with a molecule in its ground vibronic state or an excited vibronic state. Molecule makes a brief transition to a virtual energy state. Virtual state is an imaginary intermediate state. Lifetime of such states dictated by uncertainty principle. The scattered emitted photon can be of lower energy than the incoming photon, leaving the molecule in an excited vibrational state. Now, anti-Stokes scattering can also have a transition from a vibrationally excited state to virtual state. The molecule will then return to its ground state, with the scattered photon carrying away more energy than the incident photon. This is called anti-Stokes scattering. Raman scattering should not be confused with the emission of fluorescence. So that's all for vibrational mode and Raman spectroscopy. Thank you, students.